Hello students, in this session we are going to study the strain energy stored in torsion. When a torque is applied to a shaft, what is the strain energy stored, right? So suppose we have a shaft. And a torque is applied, and due to this applied torque there is some angle of twist. So by applying the torque, suppose this point moves from here to here, right? So from here to here, suppose, and this is the angle of twist in a length of L. The length of the shaft is L, right? And what is the shear strain energy stored in the material? Because the shear stresses will be developed, that's why we are saying shear strain energy. Basically this is the torque applied. So what is the strain energy stored due to torsion, right? So it is by default, if nothing is said, the torque is applied gradually from 0 to capital T value, right? So torque is applied gradually from 0 to T value, right? In that case, the total work done on the shaft will be given by the torque multiplied by the displacement, angular displacement, right? Theta is the angular displacement, you know. The work done is given by the torque multiplied by the angular displacement, right? So work done will be given by the torque, but the torque is not capital T, it is the average of 0 to T, the average of this, because we are assuming that there is a torque is applied linearly. So 0 to T divided by 2, the average of the torque applied multiplied by the angular displacement theta. So this will equal to half T theta. This is the torque applied, and this work done on the shaft by the torque will be stored in the material in terms of strain energy. So strain energy will be given by half T theta. So this is the strain energy stored in the material. This we can show by the linear variation also, that the torque is applied linearly like this. So area under the T theta curve will give the work done. So area under T theta curve will give the work done or strain energy stored. So this is the area under the curve. So area under the curve will give the strain energy stored. This is half T theta, right? Which we have written here, half T theta, right? Now, what is the torsional equation? What is the torsional equation? So we know torsional equation is given by T by J tau, the shear stress, upon R equal to G theta, angle of twist, upon L, right? So theta can be written as TL upon Gj, which is very important result. You have to remember this also, TL upon Gj. So we can put here the strain energy can be given as half T square L upon Gj. So this is the strain energy stored in the material, T square L upon Gj. Now if the torque is variable, then what will happen? If torque is variable, we are applying variable torque, then strain energy will be given as half integration of, then we have to integrate, and we have to take a small value of this dx here upon Gj, 2Gj, right? So this is the strain energy stored when the torque is variable. So from here the torque can be written as, we can replace T here, so torque can be written as T is equal to tau J upon R. This is the torque from this equation. Replace this, so you will get the strain energy, shear strain energy, as half T square, that is tau square J square upon R square, T square L upon Gj. J and J will cancel out, one J will be cancelled out. What we are getting is tau square. What is J? that is pi by 32 d to the power 4. We know that J is pi by 32 d to the power 4, right? Polar moment of inertia, that is pi by 32 d to the power 4. This should be remembered, polar moment of inertia. So this is tau square upon 2r square. J is pi by 32 d to the power 4, pi by 32 d to the power 4, L upon G, and this r can also be replaced with d by 2. So this r can be written as d square by 4, right? Solve it, and what you are getting is, solve it, and finally you will get the strain energy stored, right? And from here what you are getting is U will be equal to tau square upon suppose I am writing 4g multiplied by, this will become 2 to the 4 16, so pi by 4 d square multiplied by L, right? So you are getting this thing, the strain energy as tau square upon 4g pi by 4 d square into L. And what is this value? Pi by 4 d square L. What is this value? This is the volume of this bar, volume of this shaft. The volume of this shaft is area multiplied by length. So this is the volume of this shaft. So from here we can write U, the strain energy stored, as tau square by 4g multiplied by the volume of the shaft. So this is the strain energy stored in the material. So what is the strain energy stored? How we have found out the strain energy stored due to torsion? So we have applied a torque, and there is some angle of twist due to that torque, and the torque is applied gradually from 0 to t value. This is the 0 value, and here it is the maximum value, t value. The work done is given by half t theta, or area under the curve, that is half t theta, half base multiplied by height, so half t theta. We know by the torsional equation T by J tau by R G theta upon L. From here we can find out the theta, TL upon Gj. Put here TL upon Gj, we will get this equation. This is the strain energy stored. Now if the torque is variable, the strain energy is given by T square dx upon 2 Gj. This is the variable torque, strain energy stored due to variable torque. Now we want this form, the shear stress and modulus of rigidity relation with respect to strain energy. So what we can do is, we know that the torque in terms of shear stress is given by T is equal to tau j upon R. Put this value in this equation, we will get this thing, and finally solving it we will get the shear strain energy for torsion as tau square upon 4g multiplied by the volume.